Hi everyone, we are back and we are going to talk about pressure vessels. So, a very, very special but very relevant type of stress state. Now, you can imagine that thin walled cylindrical pressure vessels, which we're going to talk about, are obviously very relevant to a lot of oil and gas applications and other, propane tanks, a lot of those kind of the typical applications you would think of when you think of mechanics and especially solid mechanics of thin walled pressure vessels. But there are a lot of very, very, very important thin walled cylindrical pressure vessels that appear in a lot of other applications. So, for example, stents. Stents are that inflatable kind of thing you put inside of a blood vessel. Those are thin walled pressure vessels. So are blood vessels. So are virus capsids. So in your virus, it's just a thin wall that has DNA compacted inside and it wants to kind of escape and it exerts pressure on that outer wall. But the key thing here is we are going to define if we can say that it is if the thickness here, if that thickness is much, much less than my radius here, and specifically, if we say much, much less, we mean that if my radius over thickness is greater than or equal to 10, we can state that it is this is a thin-walled pressure vessel. And when we do that, we effectively, if we kind of draw this in here, we are only going to be concerned, so for example, 1, 2, 3. I am not concerned with basically the through thickness stresses. So through the thickness, so basically coming out of the board in this one direction, we don't care about the stress in that state. We're going to treat that as basically the same thing like you would treat a surface. So the variation in stress through the thickness of this thin wall pressure vessel is not going to matter. Instead, we're going to be looking at the longitudinal stress, so basically pulling in this direction in our thin wall pressure vessel, and the circumferential stress. So we can kind of see that shown schematically here. This is our thin wall pressure vessel. So we can immediately reduce it to a 2D or actually a plane stress state. Where here, if we look at this, it would be sigma longitudinal, sigma hoop, and there are only normal stresses here. So we're already in our principal stress state always for a thin-walled pressure vessel. So we don't care about the stresses through the thickness or out of the board here. So if we have a coordinate system like this is going to be essentially our system. So how can we determine what our hoop and what our longitudinal stress is? Well, we can actually do what we were just doing there. We're going to make a cut. So, for example, if I want to look at the longitudinal stresses, I'm going to make a cut that's basically tangential, or basically perpendicular. So I'm going to make a transverse cut through the systems, and I can see if I do the sum of my forces, so sum of my forces in this one direction, set it equal to 0. So I'm going to have some delta P times this circle here inside. So that's going to be pi r squared minus, so just in the other direction, again, depending on how you're actually, I'm going to set this as negative, I'm going to set this as positive, just in terms of our coordinate system. And there's going to be a reaction force when I cut along this little hoop. So that little hoop is going to be some stress longitudinal and needs to be over that area, which is going to be 2 pi r times that thickness. So that's going to be, again, the circumference times the thickness there. So that little, if we zoom in, this little area here, that little super, super tiny thin. And we're going to say that the pressure is going on that other area. I could actually draw it a little bit differently. Let's go ahead. So I'm looking at the restoring cut here versus the pressures acting on everything inside right here. So that's the pi r squared, it's just a circle, and the circumference times that thickness. So that leaves me, excuse me. Oh no. No. Let's go back to where we were. So let's go back. Come on. All right, here we go. So we can go ahead and I can state, for example, where are we at? I could determine that my sigma L, and this must be equal to 0, so this cancels, one of the R's cancels. So my sigma L is going to be equal to delta P, and this disappears, delta P R over 2T. And I can do the same thing for my circumferential here. So I could look at some of my forces in along the 2 direction. It's going to be equal, so the delta P is acting along this. So I'm going to put that as a negative, and the other one's coming out. Negative delta P times 2R times delta X plus my sigma hoop, which is going to be acting on times 2 delta X, 2 delta X times T. So my hoop is going to be equal to the 2's cancel, the delta X's cancel, so that's going to be equal to delta P R over T. So I have those relationships, and I see that my hoop is equal to basically my sigma hoop, or actually my sigma L is equal to sigma H over 2. That's my relationship. So for a thin-walled pressure vessel, the hoop stress is always going to be larger, or my hoop or my circumferential stress is always going to be larger than my longitudinal stress. So ideally, we would expect if a thin wall pressure vessel is going to fracture, it will fracture with a fracture pattern like this, because this stress will pull, and it'll fracture transverse because this is a normal stress. So if we ever see a thin wall pressure vessel that looks like this type of fracture, there's some defect or some weird things going on in there. So that is not normal. But the cool part about any thin wall pressure vessel problem is that we can immediately go into these expressions, and we also know that we're only going to have strain in our longitudinal, strain in our hoop, and our hoop strain is equal to 1 over E times sigma hoop minus nu sigma L, and our strain longitudinal is equal to 1 over E times sigma L minus nu sigma hoop. And we can solve all the rest of our problems. So be hoping for a thin wall pressure vessel type problem. And next time we are going to get into beam bending. So we will see you all next time, and we're going to get into some pretty cool beam bending concepts. So see you then.